Perfect. Thank you, Justin, and thank you everyone for being here today. As Justin mentioned in the title of my talk, basically today I'm going to kind of go over a few different projects that I've been working on and that some colleagues have been working on at the University of Oregon and the USGS regarding earthquake early warning and rapid response. The general kind of reason for this is that we need to be able to rapidly respond to a variety of types of earthquakes at a variety of scales, from local to teleseismic data, and with a variety of different instruments. Machine learning is up to the task for all of these things. So today I'm going to give a brief overview of some of the things that myself and colleagues have been working on. So the general motivation for this project, or these projects, come in kind of two parts. The first part being that we want to have accurate earthquake event products published for rapid response, and we want those products as quickly as possible. And we also want our earthquake early warning systems to deliver accurate alerts about earthquakes as quickly as possible. So I'm going to start with this kind of first subtopic here. I'm going to be talking about some of the work that I did at the USGS as a Pathways intern over the summer. What I was working on was rapid estimation of single station earthquake magnitudes with machine learning on a global scale. So as I'm sure that many people know, the National Earthquake Information Center, or NEIC, in Golden, Colorado, is responsible for detecting and providing information on earthquakes across the world in real time 24/7. And for major events that are felt by people, and some other parameters, a lot of these response information need to be published within 20 minutes. Magnitude calculation is a key part of these response publications because they're the foundation for shaking intensity estimates and also the fundamental parameter used by the public to understand the severity of an earthquake. The kind of problem here is that magnitude calculation is really complicated. There are lots of different potential types of magnitudes depending on the earthquake and monitoring setting. And each magnitude type only works over a specific range of magnitudes, and which is appropriate also depends on the properties of the waveforms. So on the right here is a snapshot from the USGS website of just a couple of the different types of magnitudes that are processed there. And an important thing about this is that mislocation of earthquakes during rapid processing can cause significant errors in magnitude estimation because those estimates rely heavily on attenuation relationships. So if you have the earthquake in the wrong location, the attenuation is going to be wrong, which can give you a really incorrect magnitude estimate. So the question that I was addressing in my internship was, can we develop a way to rapidly process magnitudes uniformly across all tectonic settings, regardless of location information, with the general goal of being able to identify large, potentially tsunamigenic teleseismic earthquakes more quickly to aid response efforts. And the strategy that we were using for this was machine learning. So before I get into the specifics of the project, I wanted to kind of give a really quick background about what machine learning is. Machine learning basically leverages the advanced computational capabilities that we've developed and statistical algorithms to analyze data, often really large and really complex data sets. There's a lot of different subsets of machine learning, but today I'm going to talk specifically about supervised learning for all of the projects that I'm going to go over. In supervised learning, you have a training data set that includes labeled examples of what the machine is supposed to learn. So for example, let's say you have a big data set of photos of cats and dogs, and you want to train a machine learning algorithm to tell you whether a photo has a cat or a dog in it. You would give the machine learning algorithm in training a bunch of pictures like these, and you would also give it labels for each picture so that it knows what it's trying to learn. You put all of this into training in the machine, it learns something about the data, and then you give the machine some new data that it has never seen before, and learning what using what it has learned from the labeled training data, it makes predictions about the new data that you give it. So if we give it these new 4 pictures, for example, the algorithm should be able to tell us that this is a dog, this is a cat, this one is a dog, and that this one is a cat. It might not always be 100% correct. And that's the kind of tuning that you do in machine learning training, is to make your accuracy as good as possible, pretty much. So one advantage to machine learning is that the algorithms can often extract information from higher dimensional data than a human can. But a disadvantage is that machine learning algorithms sometimes work like a black box, and it's hard to always know exactly what the machine is learning in its training process. So one of the backbones for deep learning, a subset of machine learning, is the neural network. They're designed to imitate the multitude of connections in the biological brain. And an example of what this looks like is shown on the right here, where you have some inputs. The machine iterates multiple times to learn the neuron weights in the machine that gets you as close to the right answer as possible, minimizing the error. So this is, a really simple example of what a neural network looks like. There are a lot more complicated things that we can do with more complicated networks. The two main types of neural networks that I'll be discussing today are convolutional neural networks, and these work better for image processing, for example, than traditional neural networks. Traditional neural networks end up with issues because of their size. So you can see in this figure here that all of these nodes are connected to each other, which makes a really big network. They also have issues with spatial information. So if you have a picture of a cat, you move it to the corner, the model is not going to know very well that it's still a cat in a traditional neural network. Convolutional neural networks use filters to learn by distilling important features out of an image. So you can see in this animation here, this filter is passing over this image, and so it can take all the information from a pixel and the pixels around it to get information about that. So it makes them really useful for image processing. We can also think of an image like a waveform in this case. So we can ask in a machine learning seismology context, for example, where is the P wave arrival in a waveform? And we can use a convolutional neural network to figure that out. Another type of neural network that I'll be discussing today are recurrent neural networks. These are nice because they can retain the temporal information of inputs to predict present and future outputs, which makes them great for time series data. The seismology application, for example, is if you have 10 seconds of data from an earthquake, what does the machine predict that the final magnitude of the earthquake is? 20 seconds later, what does it predict then? And it can still retain the information from the prediction it made at 10 seconds. So it can see how things evolve over time. So back to the USGS project that I was working on, the data set that I was given access to when I showed up at the USGS is something called Millipede. This was created by colleagues at the NAIC, specifically to expedite machine learning work with the USGS's data. And if after this talk or now you're interested in having access to these codes and the data, you can check out this QR code right here. Millipede is based on the preliminary determination of epicenters catalog that the USGS publishes. The PDE is globally complete to magnitude of 4.5 and domestically complete in the US to magnitude 2.5, and does also contain some smaller earthquakes. It has more than 5.1 million three-component waveforms from almost 190,000 earthquakes at about 2,300 stations worldwide. The waveforms in the data set are labeled with phase arrivals, and it also contains metadata about the earthquake magnitudes, the type of authoritative magnitude that a particular waveform has, and then also things like the signal to noise ratio of the waveform. And basically, this data set is specifically formatted to easily be used in machine learning applications. So it makes things really quick and easy to use. So for my project, the model architecture that I used was something called Magnet from a paper by Musavi and Baroza in 2020 in GRL. It's a combination of a convolutional neural network and a recurrent neural network like I talked about earlier. So typically in machine learning applications, you use a large set of data to train the model, a smaller different set to validate the training, and then another separate data set to test it with afterwards. So in this case, of the entire data set, we had about 75% was the training data. This is in panel A of this figure in dark blue. This is a log count histogram of the data, and it's the magnitude here on the x-axis. So in this training data, we had 2.4 million waveforms with earthquake origin times from 2013 to 2018. Our validation data was another 15% of the data set, 490,000 waveforms from 2018 and 2019, and that's in light blue on this figure. And then our testing data set was another 10%. We had kind of two pieces in this. First, in dark red, there were 320,000 waveforms from Millipede in 2020. So you'll notice that we don't have any overlapping origin times to make sure we don't have any of the same earthquakes in each of these data sets. And then we also added some historic data to the testing data set. So these are 13,000 waveforms from 2000 to 2013 that are earthquakes greater than magnitude 7.5. So those show up in light red at the edge of this plot here. And basically the purpose of including these was to see how well the model could do on large earthquakes that it didn't have in the training, because the Millipede data set currently only has data from mid-2013 to present. So there were no really big earthquakes in there to use, so we wanted to see how well it could do. So one of the other things that we use to make our model better is data augmentation. Data augmentation means operating on or changing somehow the data in your training data set to expand the number and the variety of samples that the model can learn from. This makes a trained model more resilient to problems in testing data. So for example, in a real-time seismic monitoring context, you may have instruments that have channels that aren't working properly or some issue with telemetry that prevents data from coming through. So if your model knows how to handle this by having seen it before in training, it won't be as thrown off by those potential problems. So here's an idea of what the original waveforms look like in the millipede data set. They're all stored 120 seconds long, and the wave arrival, in this case a P wave, is directly in the center of that sample. But we don't always necessarily want to have to wait a full 120 seconds to get an idea of, in this case, what the earthquake magnitude is. So we wanted to test a bunch of smaller windows of data to see how quick we could get the algorithm working. So the next thing that we did in a lot of this was we trimmed the data down to whatever window length that we were looking at the time, and you'll see the utility of that in a few slides. Another thing that we did was we randomly shifted the waveform by up to 3 seconds in either direction. So the pick was no longer exactly in the center. The reason we did this is because in Millipede, all of the picks are either performed by humans or they were at least verified and checked by humans before it went into the catalog. But in a real-time seismic monitoring context where you're just relying on automatic algorithms, the picks may not be as perfect as they would be performed by humans. And so that's why we added this random shift in, because we're trying to simulate more of a real-time application. We also added some extra noise to a lot of the waveforms. We also sometimes would flip the horizontal components. So in this case, that could be to create another source station path example, or it could simulate a seismometer that's rotated wrong and you don't have that correction put in. And then finally, we would also sometimes drop a channel or two to simulate problems with instruments, like I discussed before. So these are some of the results for the testing data that we gave to the model after we trained it. So the animation happening here is cycling through the different window lengths that we tested out, and you can see what those window lengths are in the title here. On the x-axis, we have the catalog magnitude, or the magnitude that the earthquake actually is, and then on the y-axis is the predicted magnitude by the model. At the bottom here, I've also included a histogram showing the distribution of the testing data, so you can see where there are more and less samples that we had. And so what you can see here is that as you get a longer and longer window length, more of the samples converge to the one-to-one line, which is the gray line in the middle. And the last kind of piece to this is this blue vertical line that's moving to the right with the longer window length. This blue vertical line represents the magnitude of a theoretical earthquake whose source time function fits entirely within the window of data that we were looking at. So what we think that this line is showing is that the model tends to do better if the magnitude is smaller than that theoretical maximum magnitude from the source time function length. So we think this is potentially showing some magnitude saturation issues, especially at the top end here, where the predictions at the higher magnitudes never really get all the way up to the one-to-one line. And I'll talk a little bit more about magnitude saturation and the implications of that later in the talk. One of the things that we did for each of the time windows was to plot a histogram of the error in the prediction. So in this case, this is the predicted minus the catalog magnitude. And then we could take the mean and the standard deviation of this distribution and plot this for each of the time windows. This is what this looks like, where the mean error is in black here. So we're looking for a mean error, obviously, of 0. And then the red lines show the standard deviation. 1 bar above and below is 1 standard deviation for each. So you can see that as we go to a longer and longer window length, the standard deviation and the distribution basically of the data gets closer to 0. One of the other things that we did was we analyzed performance by the hypocentral distance to see whether the model was working better with the local and regional data or with the teleseismic data. So the plot on the left here is in degrees, so 0 to 100 degrees, and then the plot on the right is just 0 to 1,000 kilometers. So it's basically just, the first kind of 10 degrees of this plot on the left. So what we can see here is that we're getting better performance at teleseismic distances than for the local and regional events. And we're still trying to parse out exactly why that's the case. So in summary for this project, we've successfully trained a model that can estimate single station earthquake magnitudes from the NEIC's waveforms. It works best from about magnitude 2.3 to magnitude 7.7 at the maximum window length. And what I'm defining as best here is just when the median predicted magnitude is within 0.5 of the catalog magnitude. Some of the next steps that we're looking into are seeing how the model works when deployed on the real-time PICs at the USGS. And then also trying to figure out what the appropriate trade-off threshold between the speed and the magnitude prediction accuracy are, and where that speed is determined by the analysis window length that we're using. So next, I'm going to go back to this problem of magnitude saturation that I alluded to on the previous slides. We like seismometers for earthquake early warning because they're very sensitive. Sure, again, many people have seen this figure before, and I've had it on previous slides, but just as a quick overview about how earthquake early warning works, we have an earthquake epicenter on the left side of this figure. And when this earthquake ruptures, the fastest wave coming out from the epicenter is the P wave, which is not very damaging. So the P wave can get picked up by these sensors like seismometers here. This information can get sent to an earthquake alert center, where an alert can be processed and delivered to people and cities before these more damaging and slower traveling S waves can be felt there. So we like seismometers for earthquake early warning because they're very sensitive and we can see the P wave arrivals on the instruments. The catch, though, is that most seismic-only earthquake early warning systems have issues during large earthquakes with magnitude saturation. There are bunch of different reasons for this. I'll just go over a couple of them. Instrument effects are one of the reasons. So seismometers typically record data by acceleration or velocity, which means that we have to integrate that data once or twice to find the displacement, which is often the information that's used to determine the magnitude. The problem is if you integrate seismic data, because of tilting and rotation of the instrument during an earthquake, you end up with these long period drifts that you can see in the red and the green here on this figure. To get rid of these drifts, you can filter the data, but then you're also removing all of the low frequency data that's necessary to characterize large earthquakes accurately. Another cause for magnitude saturation is source saturation. So this figure shows some theoretical source spectra for the surface waves and body waves of earthquakes. As the earthquake magnitude increases, the rupture time and the rise time of the earthquake increases. And because corner frequency is inversely related to rupture and rise time, the corner frequencies of the source spectra move to the left to lower frequencies as the earthquake magnitude increases. So for magnitudes calculated from surface waves, for example, we measure them at a period of 20 seconds, which is indicated by the vertical line in this plot that it's circled in green. So with smaller magnitude earthquakes, a period of 20 seconds falls into the flat part of the spectrum. So this means that the surface wave magnitude is directly proportional to the moment of the earthquake. However, with larger earthquakes, the corner frequency ends up being to the left of this line where the magnitude is measured. So the surface wave magnitude ends up being calculated lower than the actual moment would indicate. This means that the surface wave magnitude saturates around a magnitude of 8.2. So any earthquakes larger than that would just be calculated still as an 8.2. The same principle applies to body wave magnitude calculations like P waves, only that's done at a period of 1 second instead of 20 seconds, so it's even worse. Body wave magnitude saturates at around magnitude 6. So this has some major implications for accurate early warnings of large earthquakes and their effects like tsunamis. We can take an example from Japan. This is a figure from the 2011 Tohoku earthquake. Three minutes after the origin time, the earthquake was only determined to be a magnitude 7.9. So in this figure, the major tsunami with an estimated height of 3 meters or more is the red. And you can see if we look at 13 hours after the earthquake, when we knew it was a magnitude 9, the red 3-meter higher tsunami is a much greater proportion of the country. So if we had known that this earthquake was as big as it was sooner, then those tsunami forecasts would have been better. So how do we get around this? If the seismic data issues are kind of inherent to the instrument, well, we use a different type of instrument. Global Navigation Satellite Systems data, or GNSS data, don't saturate with magnitude. So that's kind of what I'm going to be talking about a lot in the rest of this talk today, is how we're using GNSS data for these applications. So this brings us kind of to the second half or second portion of this talk, where we're talking about earthquake early warning systems and how to make our alerts accurate and fast. I'll kind of talk about three different pieces of this with machine learning that we've been working on. First with magnitude estimation, then with earthquake detection, and finally denoising. So this first project is studies performed by Junting Lin, who just graduated here with his PhD from the University of Oregon. Junting has been working on rapid ground motion forecasting for large earthquakes with high rate GNSS and deep learning. He built a model called MLARGE, or Machine Learning Assessed Rapid Geodetic Earthquake Model. And his model uses an RNN network architecture with long short-term memory layers to assess the magnitude of earthquakes as they progress. He was using data for Chile for this process. He trained with synthetic data generated using a code called Fake Quakes from Melgar et al. 2016. And the reason for using synthetic data for this, which is a theme that you'll see in the next few projects as well, is to accommodate for the lack of large GNSS training data sets. Seismic data sets, training data sets for machine learning, there are a lot more of those out there, but GNSS doesn't really have the same amount yet. So we use synthetic data to fill in that gap. So Junting tested then his trained model from the synthetic data with unseen synthetic data as well as 5 real Chilean earthquakes. So this animation in the middle of the plot shows the results for the testing data with the real magnitude of the earthquake up to magnitude 9.5 on the x-axis, and then the model predicted magnitude on the y-axis. And these colored symbols here are 5 real Chilean earthquakes that he also tested with the model. You can see for one of these in the right here, the Maule 8.8 earthquake, how the model prediction magnitude evolves over time to converge towards the correct magnitude of 8.8. If you're interested in learning more about MLARGE, you can check out this paper here in JGR from 2021. So highly encourage you to go check that out if you're interested. So one of the things that Junting did in his paper was compare his model to the performance of another called GFAST. GFAST by Crowell et al. 2016 is the current GNSS algorithm that's integrated into Shake Alert, which as far as I know is very soon to be operational. GFAST estimates earthquake magnitude and depth from peak ground displacement, or PGD, scaling relationships, and it does it quickly and accurately for earthquake early warning. But MLARGE is even more accurate. It has 2 times less scatter, and it is 5 times faster. So in this figure on the right here, the columns are different time window snapshots. 60 seconds is the first pair of figures here. And you can see in the bottom panel that at 60 seconds, MLARGE is 95% accurate and GFAST is 62% accurate. So Junting kept working on this model and kept improving it. The latest version of it also now can predict the centroid location, fault size, and make ground motion forecasts for earthquakes. It can forecast this ground motion before onset, providing seconds to minutes of warning time. And it can work on large earthquakes where the hypocenter and the centroid of the earthquake are very different. So in this animation on the right, this is again the 8.8 Maule earthquake. The USGS finite fault solution for this earthquake is this pink line underneath here. And this bluish purple rectangle is Junting's model, the MLARGE model prediction as time cycles through, which you can see in the small letter here. The colors on the land here in orange are the ground motion forecasts for that earthquake. And so you can see that within minutes, it has a good idea of the fault extent and where that fault is and can make the ground motion forecasts from that. More information and warning statistics for this model will be available in Lin et al. 2023. So keep an eye out for that if you're interested in learning more. One of the things that Junting learned as he worked on this model was that the data quality that goes into it is very important. Excluding the noisy data reduces the number of prediction outliers across multiple source parameters. So the figures on the left here in the animation show what the predictions look like when noisy data is included. And then on the right, there is no noise included. So you can see that all of the little outliers that are outside of the one-to-one lines are eliminated in this no noise environment. So how do we deal with this? Because GNSS data are very noisy. GNSS early warning algorithms currently require seismic triggers because the noise floor in GNSS data is too high to see the P wave arrivals. Kind of illustration of this can be seen in this figure from Melgar et al. 2020. The orange trace on this plot is a low noise time period, green is medium noise time period, and red is a high noise time period. And if you notice the scale on the side here, this goes up to 0.2 meters or 20 centimeters. So these spikes in this noisy data here look very large. And so you can imagine if you're using a really traditional triggering algorithm for something like this, it might think that all of these things are earthquakes, which would just be really wrong and give you a lot of false positives. Another example of this comes from this figure from Brendan Crowell at the University of Washington. This is actually some data from a GNSS station in Turkey, and this shows the recent earthquake there. This is that large earthquake. And you can also see off to the side here that there are all of these spikes from this noise. And so we don't want to end up in a situation where we think that this is an earthquake when this is actually what we're trying to pay attention to. So with this noise limitation with GNSS data, we can't necessarily beat a seismic only system in terms of speed for earthquake early warning because seismometers are just so much more sensitive to the P waves. But we think that a GNSS detection system could help ensure that only good data where the earthquake can be seen are passed into source characterization algorithms like MLARGE. So this here is a screenshot from the UNAVCO real-time GPS state of health website. I took this a while back, but basically you can see here that the green stations all have lower noise, and then these red and orange stations have really high noise levels. And so if there was, for example, a big Cascadia earthquake off the coast that we were trying to perform early warning for, we wouldn't necessarily want to use the data from these stations because we can see on here that they would be really bad. So we want to make sure that if we have like a GNSS detection system, that we could only put the good data into source characterization algorithms. Having the system that works by itself would also just generally help for system robustness. So this is the problem that I've been working on the last few years at the University of Oregon, which is detecting earthquakes in noisy real-time GNSS data with machine learning. So the central question for this project is, can we design a machine learning method for identifying earthquakes in real time using the noisy GNSS data? The objectives for this project were again to use synthetic earthquakes, but also real noise from real-time GNSS data to design, train, and test a convolutional neural network with the ability to identify the onsets of earthquakes in noisy real-time GNSS data. And then we will test the performance of this CNN on a suite of real GNSS data from UNAVCO GNSS stations near Ridgecrest, California, that captured many of the earthquakes in the 2019 sequence. Machine learning methods have been successfully used with seismic data for earthquake detection in many different papers. ConvNetQuake, PhaseNet, and Earthquake Transformer are all really good examples of this. But to my knowledge, this hasn't been done with GNSS data yet. There's a paper, Kawamoto et al. 2017, used a method called regard. This was an STA-LTA detection method with horizontal GNSS displacements. STA-LTA is short-term average over long-term average. This is pretty typically used with a lot of seismic detection algorithms. The problem that they had with this was that there were a lot of false detections. So in this figure here, when they're using one neighboring site to compare with, at a triggering threshold of 3 centimeters, they had as many as 369 false detections in a 60-day test. We also took some of the data that we had from the Ridgecrest earthquakes and ran an STA-LTA picker on them. In this figure, the data for the 3 different components of GNSS data are in the colored panels, and then the black panels are the STA-LTA trigger. So if we zoom in on the time with a lot of earthquakes in the Ridgecrest main shock, which are all the red vertical dashed lines, we can see that it does trigger on one of the main earthquakes here, but there are a lot of other ones where it doesn't trigger for it at all. Or in some cases, there's a trigger and there isn't actually an earthquake that lines up with that. So generally, this STA-LTA picker doesn't work ideally with GNSS data just because of the noise levels. So what we've done for this project is we've used a UNet type CNN written by Amanda Thomas. It was designed for seismic phase picking, and we adapted it to work with GNSS data instead. We focused on the Ridgecrest, California area because there are a lot of nearby 3-component GNSS stations. We have over a year of archived real-time data from UNAVCO, and we have a wide range of magnitudes to try and detect up to the 7.1 main shock. So similar to the previous projects, we had to generate some synthetic training data for this. So we used the Ridgecrest fault geometry from Goldberg et al. 2020. And using these faults, we generated earthquake ruptures between magnitude 6 and magnitude 7.4 using the Fakequakes code. From this, we could generate 1 Hertz 3-component displacement waveforms for a set of GNSS stations in Southern California. And then we could combine these synthetic displacement waveforms like these with the actual real-time noise from the UNAVCO stations that we had data for. This ended up giving us about 700,000 total 3-component seismograms to use, and we used 90% of these in training and 10% of them for the first step of the validation process. So what does the training actually look like? In this case, the training inputs are the 3-component synthetic GNSS data and the real noise. So these basically just look like kind of your standard GNSS waveform. We also gave the model some real noise by itself, so it could learn the difference between these two. And we also gave it target information. So this target is the labels that we talked about in the beginning with the idea of what supervised machine learning is. So if there's an earthquake in a particular waveform, the target in this case is a Gaussian positioned at the P wave arrival time. So in this figure, the actual data is in blue, and then this black Gaussian is the target. And so for this particular waveform, we know that the P wave arrives right in the center of this Gaussian. If there is just noise in a waveform, the target is just an array of zeros. So using this method, the model is trained to distinguish between earthquakes and noise and identify the appropriate P wave arrival time. So when we test it in validation at the end, we test it with the remaining 10% of the synthetic data that it never saw before in training. So if the model predicts that there's an earthquake in a particular waveform, it produces a Gaussian at its chosen P wave arrival time. And if it predicts that a sample just contains noise, it produces zeros or small numbers close to 0. So here's some examples of what this looks like. This is a true positive case where there is an earthquake in the sample. The data, again, is in blue. The target is the black Gaussian, and then in red now is the prediction Gaussian that the model produced. Here's a true negative case where there was no earthquake in the sample and the model was correct. A false positive case where there was no earthquake in the sample, but the model thought there was. And a false negative case where there was an earthquake in the sample, but the model thought there wasn't. So how do we assess how well this is working? The first thing we can do is look at how well it works as a classifier. In this case, we look at the accuracy, which is the number of correct predictions that the model made divided by the total number of predictions. But the tricky thing here is that the accuracy changes depending on the decision threshold that we set, which is the minimum Gaussian height to say that the model thinks there is an earthquake. So here are 2 examples. In this case, you can think of the height of the red Gaussian as the model's confidence that there is an earthquake in that sample. So if we set a decision threshold of 0.5, for example, in this plot on the left, our red Gaussian is taller than this confidence threshold. And so it would say that, yes, there is an earthquake in that sample. In this one on the right, the Gaussian is shorter than this decision threshold. So it would say there is no earthquake in the sample, and it would be also correct. However, if we set a really low threshold of 0.1, in this case, now it thinks that there's an earthquake in both samples. So it would not be correct in the one on the right. So we can test this across the entire, threshold of or spectrum of thresholds from 0 to 1. And we find that we have the best accuracy of 98.15% at a threshold of 0.615. So then within this, what factors are affecting the identification success? So we have a 98% accuracy overall. And for the samples which represent true earthquakes, we can plot the accuracy versus the event information. So we could look at the earthquake magnitude compared to the accuracy. So the magnitude here is on the x-axis and accuracy is on the y-axis. And we can see that for the earthquakes above magnitude 6.25 and especially magnitude 6.5, we're doing really well with our accuracy in this case. We can also look at the peak ground displacement. In this case, we're plotting the log of the peak ground displacement. And this orange line that I've added to the plot here demonstrates the typical GNSS noise scale of a couple of centimeters. And so in this case, you can see that once we get to a log peak ground displacement of -1, which corresponds to a PGD of 10 centimeters, we're getting up to 100% accuracy. We can also look at the signal to noise ratio. In this plot, the different colors here are each of the 3 different components. I'm also plotting the log signal to noise ratio on this plot. So you can see that once we get to a log signal to noise ratio of 0, which is a signal to noise ratio of 1, we're getting up to about 80% accuracy on 2 of the components. And then once we get a little higher than that, we're up to 100% accuracy. So the thing to keep in mind is that right now, these accuracy statistics are based on the validation data. So this is the synthetic data that we gave the model, but it never saw in training. So what happens if we give it some of the actual real earthquake data from the Ridgecrest events? It doesn't work so well yet, unfortunately. We tested the trained algorithm on some of the real data from the area around Ridgecrest. We had 13 months of data from 278 stations. So we separated that all into 128-second segments, the same way that we did with the synthetic data. We removed about 60,000 samples that had data gaps that were over 60 seconds long. And this left us with 994,000 samples. Of these 994,000, only 2,352 of them contained known earthquakes in the catalog greater than magnitude 4.3. So that's only about 0.25% of the samples that we were using actually had earthquakes in them. So here again are some example cases of what this looked like. Here's a true positive case with the real data, a true negative case, a false positive case, and a false negative case. So we can do the same test again with the accuracies by the threshold. And it looks pretty good, right? We can get up to 100% accuracy, but this is misleading because if we only have 0.24% of the samples containing known earthquakes, if we just say that nothing is an earthquake, we're going to end up with an accuracy of 99.75, which looks really good, but actually isn't, because then we are not finding any earthquakes at all. So a question here then is, how do you pick an appropriate threshold when you can't use the same kind of metrics that we did in the previous case? And that's something that I'm still working on. Another thing that we can do then is we just look at the 2,352 earthquakes in the data set and see how many of them that we can find. And unfortunately, currently the model can only find about 7% of them rather than the 98% with the synthetic data. So here are some plots that we were trying to look at what was happening to make some of them work and others not to work. So in this case, we're plotting the picked versus the missed earthquakes by magnitude. So in this case, the earthquakes that were missed by the model are in blue, and the ones that were successfully picked are in black. So here we're plotting against magnitude. We can also look at the peak ground displacement and the signal to noise ratio. In this case, I'm just looking at the north-south component to fit things on the slide. One thing that we saw was that the average peak ground displacement of all the earthquakes in the data set was about 3 centimeters. And the average peak ground displacement of the earthquakes that the model correctly found was about 6 centimeters, so double. See something similar with the signal to noise ratio. The average for all of the earthquakes was about 1, and the average signal to noise ratio of the earthquakes that the CNN correctly found was about 3. And so generally that's kind of what you would expect, that higher peak ground displacement, higher signal to noise ratio, it works better in that case. But then there are also some weird earthquakes like this one, for example, that has a really high signal to noise ratio, but the model still missed it. So this is the kind of stuff that I'm still looking into to try and improve the performance of the model on the real data. So that's a method for trying to detect earthquakes in the noisy data. What if we could just get rid of the noise altogether? That's something that Amanda Thomas at the University of Oregon has been working on. She has built a deep learning method for denoising high-rate global navigation satellite systems data. This paper will be coming out in Seismica sometime later this year, so keep an eye out for that if you're interested. Amanda used the same synthetic displacement waveforms and real noise for the training data in this project as my GNSS picker project. And she also used a UNet type CNN architecture. In this case, it was developed to be similar to Deep Denoiser, which is a method published by Zhu and Baroza in 2019. In this case, using 3-component GNSS data instead of seismic data. For this project, they used the frequency domain information to identify and remove the noise spectrum while leaving the signal spectrum in the data. So the first column of plots in this figure on the left shows in gray, the signal and the noise combined, the noisy data. And then in blue, just the signal alone on this plot. The second column shows in the frequency domain, the mask that just shows where the signal is in this data. And so what the model is using is, this is the labels here. So the model is trying to predict its own mask, and that's the output. So in this column, this is the mask that the model is predicting. And then in the final column shows what those waveforms look like. So in this case, again, the signal and the noise together is in gray. The original signal alone is in blue, and the denoised signal is in pink. And so you can see in these panels, for example, that the pink is matching the blue pretty well. So this again is with synthetic data. What happens if you test it on the real data? This figure shows data from the magnitude 7.1 Ridgecrest earthquake, and it includes strong motion data as well as the GNSS displacements and then the denoised GNSS waveforms using 3 different model variations that are discussed in the paper. One takeaway from this figure basically is that denoising before the P wave works really well. So the P wave in this case is indicated by this vertical black line. You can see that it's nice and flat before that. But it tends to struggle with the coda. So in this case, where there is still signal after in the coda, the model tends to just eliminate it. So potential explanation for this is that there aren't any 3D wave propagation effects in the synthetic training data, because the way the synthetic training data was developed was using only a 1D velocity model. So that's a limitation of how the synthetic data was made in this case. So that kind of sums up the 4 different projects that I talked about today. So in conclusion, kind of calling back to my title, there are a lot of different promising research avenues for advancing earthquake early warning and response with machine learning. On the small to big level, we can detect and process earthquake source parameters across the magnitude scale, from looking for, slow slip earthquakes and very tiny events to figuring out how to figure out the magnitude of very large earthquakes without saturation. On the local to global scale, we've worked on uniform calculation magnitudes across many tectonic settings with machine learning supported by the Millipede dataset. And then Earth to space, naturally there are advancements possible with both ground-based instruments like seismometers and strain meters, and space-based data like GNSS data. So machine learning is a really useful tool for all of these different types of things. Thank you, and I'm happy to take any questions.
Thanks so much, Sydney. Really exciting research results there in your talk. So we appreciate you sharing them with all of us today. We have had a few questions come in already. If you're tuning in out there and you've got a question, please feel free to type that into the Q&A box. Maybe I'll just start with the first one on the list here. It says, someone wrote in and they asked, in the test for the Ridgecrest area, how many stations did you use to evaluate the performance of the prediction?
In that test, we used all, I'm assuming they're asking about the real data. We used all 278 stations there. So naturally, a lot of the stations are going to be up to, I think, 300 kilometers away from the earthquake. And so there's not going to be, much of any kind of signal showing up there from a human's eyes or potentially the computer's eyes too. So that definitely is part of the reason I think that the accuracy is so low in that case. And looking at kind of the distance there might be interesting.
Okay. Another question here from Charlie says, what would the accuracy and results for the earthquake picker look like if you used 50-50 earthquake noise only events for both training and evaluating data sets?
Sorry, could you repeat? It was jerking around a little bit in the end.
Yeah. So what would the accuracy and results for the earthquake picker look like if you used a 50-50 earthquake noise only set of events for both training and evaluating data set?
So that pretty much is what we did actually. It was a 50-50 split in the training of just noise and the signal plus the noise. And so for the synthetic data, that was also the case in the validation. With the real data, that wasn't quite the case, just because we had a certain number of samples, and I'm actually not sure what the percentage of samples with noise and without noise would be there. That kind of was what I was going with the 0.25% actually having earthquakes in them. But it was 50-50 for the validation data for the synthetic data.
Okay, great. We had a couple more questions come in here. Let's see, this one is asking about your probabilistic layer. So it says, have you used any probabilistic layer in the neural network for prediction likelihood estimation?
I'm not quite sure. I'm assuming this is still talking about the picker project.
I think
I
so.
don't, I'm not sure about that one. I'd have to look into exactly what that means.
Okay, maybe I'll jump down to another one here. Are you currently doing localization in this research, so finding the epicenter of the event? And if yes, how? I know that one of the results you showed had that characteristic. I'm curious if some of these other projects are doing that as well.
Yeah, so that currently that's only happening in Junting's project, in the M large project. I'm not trying to find any earthquake locations in mine. Mine is just detecting the onset.
Okay, and maybe a follow-on question here from the same viewer. They asked if you've considered using spectrograms at all for the CNN input.
That is an interesting idea. I have not looked into doing that at all, but that could potentially improve that. I mean, that's kind of what Amanda was going with the denoising project. It would be interesting to see if that improved things for the picker project, but I have not tried to do that yet.
Okay. We have a question here that says, great talk. Sorry if I missed this, but have you tried using metrics such as the F1 score for evaluating the results of the earthquake picker on GNSS data?
Yes, I do have figures for that. Unfortunately, I did not put them in my extra slides, but
all right, no worries.
I do have figures of that. So whoever that was, if you want to email me, I'm happy to share those with you.
Okay, excellent. Let's see here. The technical question here, what is the turnaround time for the network to process a result? And is this restricted by computing power, or does this process not require super powerful computers?
I'm curious about which project that this might be.
Well, I think you
addressing.
talked, so in looking at the GNSS results, I think it was like GFast and M large, and you were mentioning there, like, do you know what the average turnaround time is for those techniques when they're employed in the network?
When they're employed in the network, I honestly, since these were other people's work, I don't want to say anything that's incorrect. I would refer you to, here, I can go back to the slide, to this Crowell et al. 2016 paper about GFAST to look for the statistics there. M large is not employed in any kind of real-time algorithm at this point. So I don't know what the actual delay would be in terms of the processing and stuff like that. I'm not sure that that's really happened yet, but I would look into this GFAST paper because I don't want to say anything that's incorrect, since I'm not really involved with that research at all.